Today is what? 20, 27th? 20, huh? It's 37. So, I'm going to assign 2 lectures for the electrical properties and 2 lectures for the magnetic properties. Okay, and then we're going to have a final on December 13th. Final. All right? Okay. Then we want to talk about the temperature dependence of conductivity as a final topic in chapter 9. Okay. In metal or insulator, in metal case, it has too many free carriers, so we don't have to talk about the temperature dependence of the free carriers. And in insulator, we have too little free carriers, so we don't have to talk about the temperature dependence of the free carriers. Now, when you talk about the free carrier change with respect to the temperature, it has to be a semiconductor. Right? So from now on, we are strictly talking about the semiconductor properties, not the metal, not an insulator. Now, we know that number of free carriers should be, if you have available energy density state and multiplied by the probability of the electron occupancy, then this is the number of free carriers at that energy level. And then we make an integration of the energies from 0 to infinity, then it got to be a number of electrons in that system, right? So all we have to do is just solving this equation, and then we know the density of a state, Ne, is going to be 2 pi square to me square star effective mass, and 3/2, and then square root of E. Right? This is the equation that we have developed in a free electron model. And then we know the Fermi-Dirac statistics, and this Fermi-Dirac statistic is the activation energy with respect to the Fermi energy, kT plus 1. All right? Now, since we are talking about the free carriers, this is the free carriers. If you draw a free carriers in the semiconductor, then the conduction band and the valence band, and somewhere in between conduction band and valence band, we are going to have a Fermi energy, something like this, right? And then if you draw the Fermi-Dirac statistics in this diagram, at the Fermi energies, the occupancy has to be 1/2, right? So before, at absolute 0 temperature, the statistics should say the Fermi-Dirac going to be something like this at absolute zero temperature, and then at the valence band edge, it goes the probability has to be zero, just like that. But if you have a elevated temperature, more than zero, absolute zero temperature, then what's going to happen to this Fermi-Dirac statistics is that it is going to have a half occupancy here, then it is going down through the half to make the probability of occupancy at the Fermi energy to be 1/2. And then here it's going to go something like this. So these electrons occupying at these energy levels above the conduction band, okay, according to this Fermi-Dirac statistics, this is the one which can be called free carriers. We are not going to talk about any electrons in the valence band. These are the electrons which can move freely. So that is the one contribute to the conductivity of the material. Now at this tail, Fermi-Dirac statistics can be almost equal to the Boltzmann, right? And the Boltzmann statistics is nothing but E⁻ minus E star over KT. Okay? Available states and then successful electrons in the conduction band. And so naturally the E star is going to be EC minus EF, the activation energies. Activation energy for electrons to be excited to the conduction band. That is the activation energies. So if the Fermi-Dirac statistics can be approximated to be the Boltzmann statistics, then we are going to say the free electrons at conduction band, okay? The number of free electrons at conduction band is going to be some available states at conduction band, and we're going to multiply that available state by the Boltzmann statistics, which is EC minus EF as an activation energy over KT. This is the equation that we want to derive. Now let's see what's going to happen if you have NE and FE just like that. Then N is going to be integration of 1 over 2 pi square to ME star over H bar square and 3/2 E 1/2. That is the density of the states. And then we're going to put a Fermi-Dirac statistics, but instead we are going to use the Boltzmann statistics, which is going to be E to the minus EC minus EF over KT. That is the Boltzmann. So we approximate then N to be something like this, okay? Now since it is mathematically known that a square root of energy and EF over KT dE is equal to the pi 1 square root of pi and KT 3/2. That has been known, okay? And N is E pi ME star or KT over H bar square 3/2 and e to the minus EF over KT. From here, you can get this equation. Here the EF is EC minus EF. In other words, this distance is going to be called EF. All right? Then if you look back into this equation, you compare this, then we can see that NC, available states in the conduction band, is going to be two pi ME star KT over H bar square. Okay? And that is going to be called density of states of conduction band. Okay? And we can do the same thing for the holes. Let's say that is effective. Means it's not really a density of states that we can calculate, but it is same to, it has the meaning, or it means that it is the same to, it can be regarded as the density of states of a conduction band. And that's, in that sense, we just call this effective density of states, okay, of a conduction band. And if you do the same thing for the holes, then you can easily find that density of state, effective density of states in the valence band, which is 2 pi m whole, in this case, KT over H bar square, and then 3/2 e to the minus EF over KT. Now here the EF is EF minus EV, the valence band. All right. Then effective density of states of the conduction band is going to be 2 pi mH star KT over H bar square and 3/2. And that is going to be called effective density of states of the valence band. Now, if your semiconductor is intrinsic, in other words, it's a pure material, intrinsic case, N is equal to P. N has to be equal to the holes, and that is the intrinsic carrier number square. So that if you have a N here, this N, and if you have this P, you got to make a product and then make a square root of that. Then you end up with NC NV e to the minus band gap over KT. All right? So this is the empty product. Okay? That is going to be 2 pi KT over H bar square, third power M E star M H star, 3/2 e to the minus E G over KT. Then N, which is square root of N square, then it can be written as KT over H bar square, 3/2, and then M E star M H star. Three quarters e to the minus EF EG over 2KT. Okay? So this is the number of electrons, and number of holes should be the same in the intrinsic case. And we know that N is going to be expressed in the Boltzmann statistics like EF over KT, right? So if you set these two things together, and we know this NC E pi M E star over KT over H bar square, 3/2, right? Effective density of states of the conduction band. Then if you compare these two equations, then you end up with minus EF over KT should be equal to log M E star M H 3/4 M E star 3/2 minus EG over 2KT. Okay? So, EF, that is the location of the Fermi energies with reference of the conduction band, right? This EF is nothing but the magnitude, how far the Fermi energy is away from the conduction band. That is the EF. So this way we can determine the location of the Fermi energies in the system, M E star over M H star. This is a very important equation. Okay? The band gap we know, and effective mass we know. So depending on the temperature, everything else is fixed. Depending on the temperature, we can see how the ferrome energies in the system is going to be changed. So that is the dependence of the ferrome energies in the solid. Okay, this is the equation for that. And ferrome energy is electrochemical potential of the system. Okay, if you want to express your potential energies, electrochemical potentials, in terms of the electronics, then you have to use the ferrome energies. Now, if you look into this equation, let's say at absolute zero temperature, obviously this term is going out, so that the ferrome energy is always in the middle of the band gap, conduction band and ferrome energy out, and the valence band, right? At absolute zero temperature. Okay? And even at elevated temperature, if the effective mass of electrons and holes are the same, then again, you're going to have the ferrome energies at the half of the band gap, right? Now, Ni square is Nc Nv e to the minus Ef over Kt. This is the, from this equation. Okay. Ni is going to be a square root of Nc and V e to the minus E. Oh, sorry, this is band gap. This got to be band gap. This is going to be the band gap. Eg over 2kT. All right? There is the intrinsic carrier, number of intrinsic carriers. And then if you take a log of Ni over Nc, then ln mh star me star minus Eg over 2k and 1 over T. And the conductivity of intrinsic semiconductor sigma is NQ mu n plus P Q mu then it's going to be NIQ, mobility of electrons, mobility of holes. Something like this. And then that is going to be NCQ MH star over ME star, 3/4, and then mu n plus mu h, and then e to the minus eg over 2kt. That is the conductivity. So if you make a measurement of the conductivity of a semiconductor with respect to the temperature, and then make a plot in one end is NIT to the minus 3/2, and then if you plot as 1 over t in the y-axis, then you're certainly going to have a straight line and then slope corresponding to minus Eg over 2k. This is how we can determine the band gap of intrinsic materials, intrinsic semiconductor materials. Determination of band gap in semiconductor, intrinsic semiconductor. Of intrinsic semiconductor. Now let me talk about a little bit on the non-degeneracy, okay? Non-degeneracy. The criterion for this is the concentration of electron. If the concentration of electron is the same to the effective density of the states of the conduction band, okay? Then we call this non-degenerate semiconductor, okay? And then if you say the whole concentration is equal to the valence band, also we can say this is the degenerate semiconductors. For example, in a gallium arsenide, Me star is large. So that the NC is almost 10 to the 18th. Okay? So if 10 to the 17 exist in the material by doping, okay? By doping, if you can have 10 to the 17th of electrons in the gallium arsenide, then it is still non-degenerate, right? Non-degenerate. But if you put the same amount, 10 to the 17, by doping into the silicon, in the silicon case, NC is about 10 to the 16th, because due to the Me star effective density of state, effective mass of electron is smaller compared to the gallium arsenide, then it becomes degenerate. Degenerate. With the same amount of doping in the silicon. Okay, this degenerate semiconductor means it's a metal. You're going to have electrons in the conduction band as the Fermi energy located in the conduction band, inside the conduction band. All right? So far, we have discussed about the intrinsic semiconductors. And let's extend this idea to the extrinsic semiconductors. If you want to talk about the extrinsic semiconductors, then you have to know about the doping chemistry. Extrinsic semiconductors. Then you have to understand the doping chemistry. And when you say the doping, then for instance, in the silicon case, silicon atoms are having a covalent bonding with the nearest neighbors, something like this, right? Something like this. Now, if you replace means substitutionally insert the foreign materials with the group 3 or group 5, okay? Then this group 4 atoms is going to be replaced substitutionally. Substitutionally is different from the interstitially, replacement. Interstitial means foreign atom is sitting in between the host matrix, right? Substitutionally means it is going to be taken out one silicon atoms, and then the foreign atom is going to sitting right at there. So if you have group 3 element replaced by this group 3 element, then you're going to have a lack of one bonding in there. So we just call this one hole is attached to this, something like this, okay? The missing bonding. And if you have a silicon replaced by the group 5, then you're going to have one extra electrons sitting just like that. And then in ionization means the group 3 atoms is going to accept the electrons so that the group 3 atom itself is negatively charged, something like this. That is the ionization of acceptors. We call this acceptor. You accept the electrons, okay? And then group 5 give up one electrons, and then it is going to be charged positively, and then render one electrons. It's the donors. In case of interstitial replacement or insertion, then this kind of thing, it never happens, okay? You have got to be, your dopant has to replace the host atoms, host elements, in this case the silicon. All right, this is the ionization, and then if you want to draw this ionization phenomenon in a flat band diagram, then you're going to have a conduction band and a valence band. And then you are going to, if there is a Fermi energies, whatever, and this Fermi energy is going to be changed not only by the temperature, but also by the dopant concentrations, which type, acceptor or the dopant donors. This Fermi energy is going to be changed as well, okay? And then at a specific temperature, if you have a donors and acceptors, how do you locate the donor energy levels or acceptor energy levels? Your donor energy level is going to be located how far it is away from the conduction band. That is donor energy levels, ionized donor energy levels. And the acceptor energy levels is how far it is away from the valence band. So the reference for the acceptor energy level and the donor energy level is different. Always donor energy level is going to be measured from referencing the conduction band and acceptor energy level from the valence band. So if you draw something like this donor and this acceptor is, in terms of the energies, is far away. It looks far away, but in reality, if you have donors and acceptors at the same time in a semiconductor, then it is easily combined. We call that compensation. So sometimes if you draw the donor energy level and the acceptor energy level in the flat band diagram, it's just sometimes misleading. By looking at this, the donor energy level is far away from the acceptor energy level, so that the compensation may not be happen, but that is not happened in reality, because these acceptor levels and donor energy levels are referencing from different energy levels, like acceptor, conductor, and valence band energy levels. All right? Then if your semiconductor doped with the dopant donors or acceptors, if your semiconductor have enough energy from the outside, then this donor and acceptor is going to be ionized. If the external energy is not enough for this ionization, then it is not going to be ionized, of course, okay? And most of the dopants known in the semiconductor industries, in the silicon semiconductors, acceptor, we have only one choice, the boron, okay? And the ionization energy is 0.019 electron volts, somewhere around there. Now, room temperature, if you convert this room temperature into the energies, electron volts, by using Boltzmann constant, the room temperature is corresponding to the 0.025 electron volts. And this energy is big enough, bigger than the ionization energies necessary for the boron, so that if you dope the silicon with a boron at room temperature, it is ionized, okay? Most of the dopants known has the less ionization energy than the room temperature energies, so that it can be used as a dopant. Donors, we have a choice: phosphorus, arsenic, antimony, and so forth. We have a lot of choices for the donors, but for other reasons, we have only one acceptors for the semiconductors. Okay. And these donors and acceptors, they behave like a hydrogen-like behavior. Hydrogen-like behavior. Because only one electron or only one hole is connected to this dopants usually, so that the ionization energy can be represented like a hydrogenic model. This is the ground state of hydrogen, which is minus 13.5 electron volts. Okay, it's just like excitons. Exciton. We have discussed about these excitons in the absorption, right? Exciton. Exciton also involves only one electrons and one holes. It behaves like a hydrogen. And just like that, this dopant materials is going to work as a hydrogen. You follow the hydrogen model. Now, importantly, we have to realize that if you have a flat band diagram and donor energy levels like D here, acceptor energies like here. Now, you have to understand the relationship between the occupancy probability with the donor and acceptor situation. Like, now, if you have a, let's say, number of electrons at the donor levels, number of electrons at donor energy. Now, how can you derive this? You have an effective density of states or dopant concentration times the Fermi-Dirac statistics, okay? F, E, D. Then you're going to have a number of electrons at the donors. Number of electrons at the donors. Okay, that is the number of electrons at the donors. When you have free carriers, what does that mean? At donor level, you're going to have empty states and you're going to have electrons in the connection band. That is the ionization. So if your material is doped with donors and you want to know the number of free carriers, you have to calculate the N, okay, not the ND. So N is equal to number of free carriers. It's going to be dopant concentration minus ND. That is the free carrier density, which contribute to the conductivity, okay? That is the one we want to calculate. The same token, if you want to calculate the number of holes which contributes to the conductivity of the materials, that's what we want to know. And if you have a number of acceptors, density of acceptors. And then if you have a Fermi-Dirac statistics at this acceptor level, then you're going to, this is the number of electrons at donor acceptor level. Right? And these electrons, which is sitting here, where does the electrons come from? It is all come from the valence band. Okay? So this is equal to the number of free carriers. Number of free carriers. That is equal to the number of free carriers. Can you see this? Okay. So we are going to apply this for the system. We're going to discuss about it in the next lecture, which is on Wednesday. Okay. We continue discussion about this on Wednesday.